Alrighty, just making sure that audio is working, and it looks like it is. Okay, so very good. We are finally at our last unit of our geometry class. This is now section 11. We are looking at the probability and statistics units for geometry. So go ahead and take these notes down, and we're going to go ahead and get started on this first flip with the heads and tails in just a second. Okay, now, so we have this thing called probability, right? And we use it pretty regularly with words like, oh, I don't know, like probably, right? So words like probably and such are all very commonplace for a lot of us. But here we have some key points. So or excuse me, we have a keyword, I should say, not a key point, but a keyword. The keyword is going to be sample space, okay? And it's going to be the number, or sorry, the set of all possible outcomes in an experiment, no matter what the experiment is, right? So in this case, right, we're looking at 3 coins that are flipped, and we're trying to figure out what are the possible outcomes and whatnot. And it says list. We're actually not going to list them because I think it's not as impactful. So instead, we're going to make a tree diagram. Okay, so what the tree diagram looks like for us is I've already written it in red. Let's go ahead and change to a different color, say blue. And we're going to say on the second flip here, a second flip, right? What happens here is that if we flip heads or tails on the first flip, right? Then we say, oh, well, I'm going to keep my heads. I'm going to flip again. And so from that second flip, we have a possibility of 2 options, heads and tails again. So we're going to write heads and tails. Heads, tails. But just like we have a second set of options for our heads, we're gonna have the same thing happen for our tails here. So we're gonna hit the heads and hit with tails here. Okay. So there's that. But we're not just flipping it twice, we're flipping it 3 times. So we gotta incorporate another one. So let's say this is gonna be our third flip. Yeah, we have here. And just like what we did in the second flip, we're going to put heads and tails to those second flips. So heads, tails, like so, I should say. Heads, tails, heads, tails again down here. No, I can't spell. Man, I'm messing up. Heads, tails. And look at that. Keep going, man. It can get a little time consuming, a little energy consuming too. That's okay. It's okay for right now, I should say. Okay. But this is essentially what happens here, right? If we flip heads the first time, we flip heads the second time, we flip heads the third time, that is one sample space, like one piece of our sample space here. So we're going to incorporate that, okay? So what you're gonna do is you're gonna find out what the list is, right? What the list of your sample space is, but using this tree diagram to help you, right? So I have 1 possibility, 2, 3, 4, 5, 6, 7, 8 possible outcomes. It's going to be our answer. Okay, 8 possible outcomes for 3 flipped coins. Okay, just like so. 3 flipped coins has 8 possible outcomes here. Okay, so that's the start of it. And we will keep on going. Not only can we see a sample space with flipped coins, but we can also see the sample space with a spinner, for example. So in this different experiment, we have a spinner to the right, a spun. And part A says, how many ways can we spin a 1, 2, 3, 4, or 5? Well, the easiest way to do it is just to count. Look at the spinner. How many instances do you see a 1? How many instances do you see a 2, et cetera, et cetera, et cetera. So we'll go. Let's see. We have 1, 1, I think. Right? 1 way for 1. Then for 2, there's 2 ways. Right, so we're taking out this one, we're taking out this one, taking out that one. For 3, there are 1, 2, 3 ways. For 4, we have 1, 2, 2 ways. And then for 5, we're going to have 1, 2, 3, 4 ways. Okay. And so if I spin the spinner, it tells me to list the sample space. Well, if we were to treat each one of those individually, like one piece of the entire thing, so what essentially I'm saying here is that this 5, right? This 5 is different from this other 5, right? We're just making the distinct different regions. It's basically to say, well, list out every single possibility. So I have 1, 1. I have 2 2s, right? Looking back at part A, I have 3 3s. And I have 2 4s. And then I have 4 5s. Right? Getting a little confused there. Okay. And so if I were to figure out, well, I can just count however many possibilities here, I'm going to have 12 outcomes. Okay. That's pretty easy. Or at least I hope it's pretty easy. There you go. Now, all this, of course, we're talking about probability, so we'll get to more probability shortly, but this is kind of like what we can see from just exploring. Okay. But we'll get into the real nitty-gritty stuff with key point 1, where we have what's called a probability experiment. And anything that is possible that happens here is called the outcomes. And so we have, for example, a regular dice, right? You have 6 possibilities, 6 outcomes, and then each one is called an event. Okay. A collection of outcomes is called the event. And then setting up, or the set of all possible outcomes is called the sample space that we discussed beforehand. So let's say we are looking at example 1. We are looking at flipping a coin and rolling a 6-sided dice. Now, something to clarify is that you always do the first event first. So this is our first event. First event. Then this is going to be our second event. Second event. How many possible outcomes are there in the sample space? List the possible outcomes below. Okay. Well, luckily for us, this can be pretty easy. So we're going to say, well, it tells us to flip a coin. Well, in the coin, it only has heads or tails. So we'll write heads up here. We're going to write tails over here. That's going to be for our coin. Right. And so I guess for that matter, let me go ahead and erase this so that we can color coordinate. Right. So this is our first event, like so. And then I'll change the color back to green so that we can see it much more clearly. Right. And so we have our second event. We have the dice. And it has possibilities of 6 different options, 1 through 6. Well, if I flip the heads, I could have a 1 with the heads, a 2 with the heads, a 3 with the heads, and you can kind of see where I'm getting with that. All right, 1 through 6. But the same thing is going to be applied to our tails here, where we have 1 possibility for a 1, a 2, a 3, a 4, a 5, and then finally our 6 here. Okay, so this is what it's going to look like for us, like so. And so after we've done all that, we can count the number of outcomes. We can see heads 1, 2, 3, 4, 5, 6 is 6 outcomes. Tails 1, 2, 3, 4, 5, 6 is another 6 outcomes. Add them together, we get 12 possible outcomes. So 12 possible outcomes. Sorry. So we have this idea here with 12 possible outcomes. And that's it. That's all that this question wanted us to do. Just showing it a little bit different. But then we have this example, right? We have extra example 1. We spin the spinner, right? That's going to be our first event. So let's go ahead and look at our spinner now. All right, we have 1, 2, 3, 4, and 1, 2, 3, and 4 possible outcomes here. And this is where it gets a little tricky, right? beforehand, I always told you that geometry you can't assume. However, in this case, we're going to assume that these are all equal to each other. So each space is equal to each other. So we're going to write the spinner. So spinner 1, 2, 3, and 4. And then we'll do the same thing for our second event. Our second event is going to be flipping a coin. Right, second. How many possible outcomes are there in the sample space? List the possible outcomes. We'll do the same thing that we just did in the last problem. So, flip a coin. Go heads, tails, you go heads, go tails, go heads again. Oh man, wow. Tails, heads. My handwriting is getting slightly more sloppy. Man, this is not that great, right? I think we can all agree that this is not as fun as we may think. Actually, it might be more fun to just spin the spinner and flip the heads or flip the coin. But here we are. Okay. But we did find our outcomes, right? And so our outcomes here is going to be 8 possible. That's just counting. Possible. Okay, very good. Now, obviously, you're watching the video means that you probably don't have a neighbor around, but I want you to think to yourself then, would you want to roll 2 dice for the potential outcomes? Like, really, would you want to do it? Like, for sure? What about 3 dice or 4 dice? And so something I want to kind of like look at is, let's think back to that coin example first. I think it'd be easier to think about this first. So we're going to go back slightly to this example where we had 8 possible outcomes for 3 flip coins. Well, we'll apply that to what I'm going to show you here. Okay. There's going to be an easier way to figure out all the potential outcomes for these EC possibilities. Okay. I can't clarify enough that this is going to be for easy possibilities. Not every single thing is going to work with this. Okay. So if I were to flip one coin, I had 2 outcomes. Right. That's just from us saying, oh, well, I have heads or tails. But I only flipped it one time, the one flip. But if I did 3 flips, I had 8 outcomes. Okay. And this is actually going to help us. We have to figure out what the relationship is between 2 and 8 that gives us this many. Okay. And I know a lot of us are going to think, oh, well, 2 times 4, right? But what does 4 have to do with this entire equation? Right. I went from 1 flip to 3 flips, right? So maybe it's just the number of flips I'm doing, possibly, right? Maybe the number 3 can help us here. Well, if I think, the number 3 is going to help me here, how do I get from 2 to 8? Well, 2 cubed is actually going to be equal to 8. And so if I say 2 cubed equals 8, right, we can actually see something a little bit easier. Okay, so we'll come back to this. Now, imagine that we're dealing with a dice. Okay, so if I had 1 roll, there are 6 outcomes, right? 1 through 6. But if I take the same approach as this coin business up here, right? Let's say I had 2 rolls. Well, in order to figure out what that would be, I'm going to say, well, 6 outcomes for 2 rolls is going to give me 6 squared. That's going to be 36. And what you'll find is that this is correct. Okay. So for 6 outcomes and you roll it twice, you're going to get 36 possibilities, 36 possible outcomes here. Okay. So that kind of brings us back to the question of, would you want to find 36 outcomes for rolling 2 dice? I don't think so. I don't think a lot of us would want that. But then you think about it even further, right? If I were to do this for, let's say 3 or 4 rolls, let's see what that would look like for us. Let's see. So if I had 6 to the third, that's gonna be 216. But then if I had 6 to the fourth, that's gonna be 1296. And I think a lot of us really don't want to do this T chart or this tree diagram. Don't, man, don't do that. All right, don't do that. Okay, don't make it more difficult on yourself. Okay, so the lesson that, or the illustration point, the point I'm trying to illustrate, that's the word. No, that's the phrase I'm looking for. The point I'm trying to illustrate here is that there's an easier way to do this. Okay, an easier way to figure out the possibilities, the amount of outcomes possible. Okay, and you're basically going to take the number of initial outcomes, put that in parentheses. We have the number of potential outcomes, and you're going to raise it to the power of events, or rather, I should say, number of events. This up a little bit. Number. It's a little bit easier. Number of events. Okay, and we can see that to be true because, well, if I have 6 possible outcomes for every one roll, it's going to give me 6. If I have 2 outcomes for every one flip, I have 2 outcomes, and so on and so forth. Okay, so that's the point I'm trying to illustrate. Again, this is not going to work all the time. There are some things that are going to work easier, but for right now, you can safely rely on this for simple possibilities. Okay, so like flipping a coin a number of times or rolling a dice a number of times. But it won't work necessarily with like 2 different distinct things, like a spinner and a coin, or a coin and a dice at the same time. So it might be a little bit trickier to do that, but we will learn something to make this a little bit easier for us later on. Okay, but for now, just kind of keep this in your mind. Now, this is just a lot of notes and such, but just to kind of reiterate, right, we're looking at probability and such, and so we're looking at how likely something is, how likely something is not, and looking more specifically at the favorable outcomes, right? So if I rolled, let's say I was, or rather the examples here, right, if I'm flipping a coin and I want tails, what is the possibility that I'm going to get a tails? Well, I have 2 total options of heads or tails, and tails is one of them. So I have 1 favorable outcome tails for every 2 total number of outcomes. Okay, so it's a little bit tricky to understand, maybe a little bit, but you'll catch on. Okay. And just to clarify, this P of A, that is the probability of event A happening. And event A is the favorable event. Okay, so event A is favorable, and then the bottom is going to be the total number of outcomes for our equation. Or sorry, not our equation, for our possibilities of outcomes. Okay, so you can we can do this think pair share, but we're actually going to look at the next example because it's going to have us like have all the work and such. It's not required of you to do every single thing under the outcomes column, which you'll see now. You don't have to do everything under the outcomes column. It might be helpful maybe later on, but you don't have to. But what I do want you to do is copy down the number of correct. So the arrow and the 1 way, 4 way, 6 ways, 4 way, 1 way, all that stuff. All that stuff. Okay. Now, with the way that this problem was made, it wanted you to do essentially the outcomes, like mark all those X's and correct marks and such. I didn't want y'all to do that because I think it's just going to be a large waste of time and it's just not going to be as fun. Okay. So if I was looking at this and I'm looking at the probability of guessing 2 questions correctly, I'm going to write 2 to kind of use the notation that we were using, this capital P of event A, which event A is exactly 2 correct. Okay, and you'll be very clear. You don't want to just say 2 correct because it's not specific enough, right? 2 correct, like more than 2 correct, exactly 2 correct, or less than 2 correct, right? You have to be very specific. So make sure you're writing exactly 2 correct. But if I look here, I have 6 possibilities, and I count 1 plus 4 plus 6 plus 4 plus 1. That's going to give me 16. And so if I have 6 favorable over 16 possibilities, that's going to give me 3 or 8, which is equal to 37.5%, if you like percentages. Fractions, percents, and decimals will work. It's completely up to you, however way you want to represent your answer. So long as it's the right answer, though. Okay. But the thing is, right, is that we wouldn't have known that the possibilities were 16 if we didn't know the shortcut that I just showed you, or if we did this, right? This whole thing. And I didn't want to do that whole thing with you guys again. I just explained that explained why I didn't want to do that. But this is going to save us a decent amount of time. Okay, instead of doing all this X's and check marks and such. But then we look at this extra step before, right? We see this coin and we want to flip 4 times. There's an easier way to do this, right? We're going to take the same principle that we just learned here how to do, but then we're going to take the same idea that we're going to do. Oh, no, sorry, right there. We're going to take this same principle too, but then apply it to a problem that is going to be a little bit easier for us. So we said that we take the number of initial outcomes, which is 2 in this case, right? 2 is in the heads and the tails. Put that to a parentheses with the exponent of the number of possibilities, or the number of flips in this case, is going to be 4. Well, 2 to the 4th is going to be 16, right? And just to clarify, just so we're very sure about how we know all this, sorry. The board is not cooperating with me. Hello, board, please. Board. It's not working with me. Hello. Okay. Be really cooperative today. Oh, board. Why is board not working? Okay, I guess it really doesn't want me to change the color or something. Huh. Okay, let's see. Hold on. Let me figure it out right here. I don't know where my mouse is. There it is. Okay, so bring this up. Still not quite what I wanted, but okay. Well, I guess we're gonna rock with blue for the rest of the class or the rest of this lesson because I don't know why it's not working. Okay. Well, the coin, of course, we said has the heads and tails. And that's where this goes in. And we're flipping 4 times. That's where the number of events that we're doing. Okay, just to clarify. What is the probability that it lands on heads exactly 3 times? Okay, well, 16 is the total. Okay, and like I said, instead of doing this whole thing, we're gonna make it a little bit easier for ourselves. We see that we can have 3 possible heads here. So let's just list out the 3 possible heads that we could have. So heads, 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 tails, right? There's only 2 possibilities. It's got to be heads or tails. Well, heads, heads, tails, heads, heads, tails, heads, heads. Then we have tails, heads, heads, heads. Okay. And obviously we can count that. We only get 4. So we get 4 over 16, right? The probability of getting exactly 3 heads. 3 heads. That's going to equal 4 over 16, which of course is going to equal 1 over 4, which equals 25%. Just like that. Makes things a little bit easier for us. There you go. Okay. Cool. Then we have this. This is it's not useless, of course not, but it is not always necessary. Sometimes it's easier to do one way or the other way. So it really just depends on how you're feeling. But you know, in a situation where you need it, it may be easier to find the favorable outcome and subtract it from 1 to find the non-favorable outcome. And so just to clarify, like this A and A bar, they're like complete opposites. Okay, so let's say, for example, I'm looking to roll a 3 on the dice, right? My favorable outcome is the 3 on the dice, but then my non-favorable outcome is literally anything else. So 1, 2, 4, 5, 6. Okay, so I have a 1 in 6 chance to get a 3. I have a 5 in 6 chance to not get a 3. That's the kind of idea that you're working with here. Okay, so we'll work with that idea. Something I want to clarify too is that this star here is indicating that we have a question like this on our quiz. It's our final quiz of the year. So I want you to really put a star next to this and reference it back from time to time to review for your quiz. Okay. When two six-sided dice are rolled, there are 36 possible outcomes as shown. Find the probability of each event. Okay, the sum is not 6. Well, you can do it one of two ways. You can set it up as that A bar, or you can figure out as, as well, like what is not 6, or sorry, yeah, what is not 6. Okay. And that kind of just depends on how you're feeling, right? If I look at this problem, I say the sum is not 6. All right, that's my favorable. That's what I want. So the sum is not equal to 6. That's what I want. And so what I'm going to do is I'm going to look at this diagram here on the right side. And I'm going to find all the dice that equal to 6. So this one, this one, this one, this one, and this one. I don't think anything else does. Yeah, I believe so. Well, if those 5 do not equal 6, do I think it would be easier to count the numbers that do not equal 6 or the numbers that do equal 6? Realizing that I have just now counted the numbers that are 6, right? Do you see what I'm saying? Right. So if you're looking to figure out P of not 6, the way you're going to figure it out is going to say, well, 1 minus P equals 6. That's one way to do it. And so in order to do that, I'm going to say, well, the probability of not equal to 6 is equal to 1 minus, and I have 5 possibilities of equaling 6 out of a possibility of 36. And it's going to give me 31 over 36, which is 86%. Okay, again, you can represent it as a fraction or a decimal or a percentage. So P of not equal to 6 equals 86%. Oops, 86%. Okay, just like that. Just like so. Then we have B, which is very much the same kind of question. The sum is less than or equal to 9. So what you want is less than. So you want 9 to be on the larger side of that kind of arrow. And then you have that equal, so you're gonna have the little bar underneath. Okay. So after you figure that out, you're going to then say, well, do I think it's gonna be easier to count numbers less than 9 or numbers above 9 and equal to 9? Okay. So in this case, I'm gonna look for the numbers that are 9 or that equal to 9, and it's gonna be these couple. All right, cool. It's gonna be this one, this one, this one, and this one. And again, I'm looking at the ones that are equal. So that's those 4 numbers that's equal, and I still need greater than. So 1, 2, 3, 4, 5, 6. And so if I'm looking for less than 9, I have just found everything that's equal to or greater than 9. So I get 1 minus my probability of finding anything greater than or equal to 9. And that's going to give me this. The probability of less than or equal to 9 is equal to 1 minus 10 over 36, which is going to give me 26 over 36. Like so. Oh, I apologize. You're not going to include the equal to. Okay, I thought it was looking weird. Okay, you're not going to include the equal to for the probability of greater than 9. So instead of having those 5 that we just found, we're actually going to have 6 instead. So we do not have 10, we have 6. So it's not going to be 26, it's going to be 30. I thought that looked weird. Okay. Which means that our probability of less than or equal to 9 is going to be 30 over 6, or sorry, 30 over 36, which is 5 over 6, which is equal to about 30 or 83% like this. Okay. Go ahead and try extra example 3. Then come on back. The sum is greater than 8. Again, we're going to keep that same idea here. We want greater than 8, so away from 8 here. 1 minus the number of 8s. In this case, again, do you want to figure out what is greater than 8 or which one is less than 8? Luckily for us, we know that this line right here is going to be our equal to 8. And it looks like it's going to be easier to count the ones that are larger than 8, which is what we want. And so if we want to find our larger than 8, we're just going to count all these different possibilities, in which case we're going to get a 10. Well, I'm looking at my notes and something's not right here. So we want to find the sum that is greater than 8. That's our favorable outcome. So that's going to be the 10 over here. So 10 over 36. That's going to reduce down to 5 over 18. And that's going to be some percentage I can't think of off the top of my head. About 30%. Okay, so about 30%, something like that. Good. Yeah, because I think in my notes I have it a little bit different on mine. Okay, so we're just accounting for the little bit of difference. Okay. Then we have our part B. The sum is not 2. So P of not equal to 2. And of course, we only have one that is equal to 2, which is this pair, which means that anything that is not 2 is going to be 35, because we don't want 2. We want everything that's not 2, in which case 2 is the only number that is by itself, other than 12, of course. Okay. And that's that problem. We do have a little bit more notes. This is our last key point of this section here. Again, I don't know where my my little dashboard here is anymore. It's not here. It's upsetting. It's okay. But we have this experimental probability, and then we have the number of trials. Okay. So something I want to clarify with this here too is, let's say I have a 6-sided dice. Right? 6-sided dice. Okay. And this dice obviously has 1, 2, 3, 4, 5, and then 6 possibilities. 6 outcomes, if you will. And I were to say, what is the probability of me getting 6? Right. Well, just like we talked about before, right? The probability of getting a 6 is just one favorable outcome over the number of possibilities, which is 6. Well, that's not necessarily how it always works in practice, okay? And so if you were in class, we had some dice here that we were messing around with, right? And I have a dice in my hand now. Let's say I'm looking at the experimental probability, right? Let me just clarify as well that this is going to be the theoretic probability. And just let me clarify that part. We have the theoretic probability. Then we have like the experimental, where we have the equation up there, where it's the number of successes and then the number of trials, right? So we're looking for the probability of 6. Let's say we do it for, let's start off easy. Let's say 1 trial. So I have a 1 in 6 chance to get a 6 on this trial. Let's see what I get. And I get a 3. Okay, that is considered a non-success. So I get 0 up here for my number of successes for my 1 trial, and I get a 0 for my probability. That's experimental. Now let's bump it up. Let's say I had a probability of, probability of 6. Well, let's say I had 6 trials. Theoretically speaking, I should get at least 1 6, right? At least, theoretically speaking, or sorry, not theoretically speaking, I should get exactly 1 6 theoretically, but we'll get there. I roll. I got a 5, so that's not a 6. I got a 1, that's not a 6. I got a 2, that's not a 6. I got a 1 again, that's not a 6. I got a 4. And I got a 3. So out of 6 rolls, I got 0 6s. 0 6s. And so this is what we call undervaluing the theoretic probability, right? We're not getting theoretically what we should be getting. Okay. But there's also a possibility that we're getting over the probability. So let's say, for example, we had probability of 6, right? Just like we normal. And let's say we have 6, right? We'll just stay with this number. But then I rolled and I got 3 6s. That's 1/2. That means my experimental went over by quite a bit, actually. You know, you're considering 1/6 in comparison to 1/2. Like that's a pretty decent margin, right? By a whole third. So what that tells us is that, well, essentially, we don't always follow the theoretic probability. Okay. And so something I would clarify again is that, you know, the theoretic probability is like the mathematical way. Mathematical. Mathematical way. That's like perfect. In perfect conditions, it's always going to have this theoretic probability. However, in the experimental, this is the realistic way. Okay, where there's going to be some variation. There's going to be some unders, some overs, and some exacts. And we're going to see that in another example here coming up. But I want you to think about it like this. And the last thing I want you to leave you off here with your key point 4 is I want you to know this term. This is what we call the law of big numbers. Okay, and what the law of big numbers basically tells us is that with enough trials, the experimental probability will level out with the theoretic probability. What does that mean for us? It means that in my sample of 6 trials with no 6s rolled, let's say instead of 6 trials, I made it to 6,000 trials. It more likely than not is going to end up being 1 out of every 6 dice rolls, I'm going to get a 6. Okay. And this will work for any probability. Flipping a coin will generally always be 50-50 with enough trials. Rolling a dice will be 1 out of 6 with every trial. Looking at one of the spinners that we had, right, the 1, 2, 3, 4 spinner, that's going to theoretically have 25% for each of those different numbers there, right? This is going to work for any kind of probability experiment. Okay. Eventually, of course, eventually, with enough trials. Now, with that in mind, we have one last problem. Each section of the spinner shown has the same area. The spinner was spun 20 times. The table shows the results for which color is the experimental probability of stopping on the color, the same as the theoretic probability. Okay, so we look at this, we're going to think, oh, well, I look to the right-hand side and it looks like each one of those colors are about the same. So we're going to figure out what the experimental probability is, or sorry, the theoretical probability first, and then we'll find the experimental. So theoretically speaking, there are 1, 2, 3, and 4 options. They are exactly the same, we'll just say. So the theoretic is going to be 1 and a 4. So 1 theoretic probability is that out of every 4 spins, you're going to have 1 blue, 1 yellow, 1 red, 1 green, and such. Okay. So we look at our spinner results. We get 5 red, 9 green, 3 blue, 3 yellow. Okay. And we'll say here, well, let's add them all up, right? And see how the number of trials we had. So 5 plus 9 is 14, plus 3 is 17, plus 3 is 20. So 3, or sorry, not 3, 20 trials. We'll look at red first. Well, red had 5 successes for 20 trials. That's 1 out of 4. Okay. That does match our theoretical probability. That's going to be a check mark. Then green had 9 out of a possible 20 trials, 9 successes out of a possible 20 trials, which this is going to just be 9 over 20, and this does not follow a theoretic. And since blue and yellow are the same thing, we're going to go ahead and lump them together, blue and yellow. And equal 3 over 20, which just is equal to 3 over 20, and that does not work. So red is the only one that follows the theoretic with its experimental probability. Okay. But then I pose a question to you. Let's say I were to, kind of mess around with the spinner a little bit. Let's say I would look at the sensor and I want to take this portion here. You know what? Actually, make it a little bit easier for ourselves. We'll look at it this way. Okay, just be there. Yeah. Okay, let's pretend that I have blue right here. I'm taking over half of yellow. That's going to influence my new, my new probability or theoretic probability for blue and yellow, but it's not going to change for my red and green. Red and green did nothing or had nothing involved with this, but blue and yellow is changing either 1 for greater or 1 for less. So because of this, blue is going to have a higher theoretic probability than yellow will, and blue will have a higher theoretic probability than red and green as well. Okay. So kind of keep that in the back of your mind that, things aren't always going to be perfect, right? Going back to that first spinner question that we had where we had like 1, 1 and 2 2s and 3 3s and such, right? A lot of the time you're going to probably have a spinner that looks more like this one than perfect, but it's either going to be perfect or it's going to be imperfect, right? That's kind of the duality of it, right? But that is essentially the idea that we're working with here. And that's all we got. Okay, that is the first section of Unit 11 down. And well, I hope that this was very helpful for you and whatnot. And I look forward to seeing how well we would do on probability and such, because I think probability is really interesting. And I think a little bit more interesting than what we were doing beforehand, especially with those proofs and such. But yeah, that's all I have for today. We'll see you next time, and I hope you have a good day. Bye-bye.